is the force on the electron divided by its mass, and the mass of the electron is, again, you can look this up in online. Okay. So this is 12 and 5, 17. So 10 to the 17 meters per second square. All right, and okay, so the electric force on it is a million billion times the weight of the electron. 4 million billion times. So anytime there's an electric force, you can totally ignore the gravitational force. Yeah, so that's the that's G's. Okay, 4 million billion G's is the force. Yes. So 4 million billion times the weight of the electron. Yeah. So when the electrostatic force is acting, you can ignore gravity. Yeah. All right, so here's a couple of problems where we set up integrals. Okay. Okay, this problem says a total charge Q is distributed uniformly along a thin straight rod of length L. What is the electric field at point P1 and point P2? So what is the electric field at point P1 due to these charges and at point P2? Okay. So you know the electric field due to a point charge at distance r. So if the electric field is kq by r squared. Okay, that's the formula. Okay, so now if you want to calculate the electric field due to this rod at this location, what we'll do is we'll break this rod into little pieces, symmetric pieces. Okay. This piece will have an electric field in this direction. This piece will create an electric field in this direction. Since the charges and the distances are the same, those two electric fields will cancel each other. And then we'll break it up into this piece and that piece. So you see the net electric field at the center is 0. Okay? So that was easy. Yeah, so that's just from a symmetry argument. Now, so B, now we'll calculate the electric field at point P2. This is distance A, this is L, and we'll set our x-axis like that. All right, so let's say this is dx, this is x. Okay. All right, so the charge, that's the charge due to this guy is dq. Okay, this charge is producing an electric field at that point. Okay, and we'll say that electric field is dE is k dq, the charge, divided by r squared. R is this distance. Okay. And what is that distance in terms of the quantities that we have written? Okay, this is L plus A minus X. L plus A minus X squared. Yep. All right, so I'm going to, actually what I'll do is I'll copy this thing. All right, well, let's write dq. dq is the charge. Okay, so this is a linear charge density. The total charge is q. Q by L gives you the linear charge density times dx gives you dq. Okay, the fractional length dx by L times q gives you the charge on that little thing. Okay. So the electric field at this point, dE, the electric field at this point due to this charge is, we're going to put all of that in, K Q over L, L plus A minus X squared dx. Okay, so what we have shown is the electric field due to this guy at this point is that. The electric, and all the electric field vectors are pointing in the same direction, so all you have to do is add up those magnitudes for the total electric field. Okay, what does adding up mean? Doing an integral. An integral is adding things up. Okay, so the net electric field is the sum of all those little electric fields, which is equal to KQ over L, L plus A minus X squared dx. All right, what are the limits of integration? 0 to L, okay? So X needs to go from 0 to L. That's where the charge is distributed. Okay. KQ by L are constant, okay, so dx L plus A minus X squared, okay, 0 to L. Okay, and the integral of this is 1 over that. So KQ over L, 1 over L plus A minus X. You can see this if you bring this to the top, minus 1, so the derivative of this would be 1 over this square, and then you would get a minus 1. Okay, so this is the integral of that, okay? And the limits are 0 to L. So the electric field at that point is, for the upper limit of L, that becomes 1 over A. So KQ over L, 1 over A minus, for the lower limit, X is 0, so it's 1 over L plus A. Okay. All right, so whenever you do a long calculation like this, what you want to do is check if your answer is right by doing limits. Okay, so let's see how can we do this. Okay, so here in the limit L going to 0, this becomes a point charge, and you're finding the electric field at a distance A. You're making this a point charge. Okay. So in the limit Oh, well, actually, I guess we'll have to be a little careful now. All right, so okay, so now we can do the limit. Okay, so this is equal to that. Did you guys understand what I did? I just added those two. Now we can take the limit. In the limit L going to 0, that becomes a point charge, and the field is just kq over a squared. Limit L going to 0, it's kq over a squared. Okay. So this is the correct expression. Okay. Oh, well, it has the right limit. Okay. All right, so we'll do one more problem. Okay. We'll set this integral up. Okay. Okay, again, so a rod bent into the arc of a circle. By the way, so we did this problem, we calculated the electric field here. If you wanted to calculate the electric field here at this point, that would be impossible. That would be very hard. Only along axial points can you calculate the electric field. Okay? So only along symmetric points, it would be very hard to do this. Okay? So similarly, we are going to calculate the electric point at the center of the semicircle. Any other point would be very hard to do. Okay? All right, so again, we'll calculate the electric field due to this guy and due to this guy. Due to this guy, the electric field is pointing in that direction. Due to this guy, the electric field is pointing in this direction. And you can see that these components will cancel, and only these components will add up. Okay? So we'll be adding a whole bunch of numbers, meaning we'll be setting up an integral again. Okay? And again, if you try to calculate it at any other point, these components wouldn't cancel, and then you would be adding a whole bunch of vectors, which will be very hard to do. Okay? All right. So here we go. Let's calculate. So let's say this is dE. Okay, so this is dQ, and again I will, and dE is k dQ over r square. R is constant. dQ is okay, so rod bent into the arc of a circle subtends an angle of 2 theta at the center P. If the rod has a charge Q, so dQ is Q over it's okay, so this is dQ. That's the angle subtended by this guy, d theta. Okay, so d theta divided by the total angle times q gives you dq. Okay. All right, so dE, the field due to this charge at this location, dE is k over r squared times q d theta over 2 theta. So that's this field, and that's at an angle theta. Okay, so again, we'll call this angle phi. We'll call this angle phi. This angle is phi. Okay, so what we want is just this component, so cosine phi. So we'll call that the y component, dEy equal to dE cosine phi. Okay, so by the way, so this is d phi. This angle is d phi. Our variable is d phi. Okay, so dEy is k over r square q over 2 theta d cosine phi d phi. All right, so that is the y component of the field due to this small angle d phi at this location. And then you just add up all over. Okay, so the total electric field, and that's in the y direction, is dEy. Okay, so let's do that. So Ey k r square q over 2 theta cosine phi d phi. Okay, and so what is the limit? What are the limits of the integral? So this angle is phi. Okay, so it goes from 0 to 2 pi. Okay. 0 to 2 theta. 0 to 2 theta. Or okay. So hang on a second. This is phi. Okay, so no, we have to do it. Okay, so this is theta, this is minus theta. So actually we'll do it like this. So minus theta to theta. Okay, so this angle phi, oh this is phi. This angle is phi, and that angle is phi. Okay, so phi goes from, this is 0 phi, this is theta is the maximum value there, and minus theta is the maximum value here. Okay. All right, so that's the integral. All right, so this k r square is constant, q 2 theta is constant, and the integral of cosine phi is minus sine phi. Okay. And this is theta and minus theta. K r square q 2 theta is minus sine theta and minus of sine minus I'll pull out the minus sign. Sine theta minus sine minus theta. And sine, that's minus, so it's minus k over r square q q 2 theta 2 sine theta. Sine of minus theta is minus sine theta. Okay. Okay, so this the 2 cancels. Okay. So EY is minus K Q over R square sine theta over theta. Okay, the negative sign just telling you that the EY component is pointing that way in the downward direction. Okay, so let's see if this expression is correct. Let's check out a limit. Okay, so if you, and the way to check the limit is in the limit theta going to 0. In the limit theta going to 0, what happens? This becomes a point charge. And the field due to this point charge at this distance is kq by r squared. In the limit theta going to 0, sine theta by theta is 1. And the field becomes that of a point charge. Okay? So it has a correct limit. All right, so that shows you how to set up integrals to calculate the electric field. Okay, again, like I said, we showed you how to calculate the electric field due to this uniform charge distribution at this point. And again, like I said, it would be very hard to calculate the electric field at any other point. In this problem, we showed you how to calculate the electric field due to this guy at this point. Any other point, it would be almost impossible to calculate. Okay, so calculating electric fields due to a charge distribution is hard. It's hard to do those integrals. Okay? And the next chapter, that's what the next chapter is about, calculating electric fields for various charge distributions. And Gauss's law will help you do that, except that you will be able to calculate the electric field only for symmetric charge distributions. We'll set up an integral, okay? And that's what the next chapter is about. Okay.